Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 29. We will be now discussing a case of a thin section mold with the mold is metallic and primarily the thermal conductivity of the mold is much larger in comparison to the metal which is being solidified, and we would also try to estimate in this condition what is going to be the solidification time. Okay, so we have so far covered two different cases. Just to recall, one was a plain sand casting where we assumed perfect wetting condition and then we introduced a non-wetting condition and then tried to estimate the heat transfer assuming a interfacial resistance because of a thin air film formulated between the casting and the surface. So in this particular case we are having a small thin section mold with a large casting which is predominantly the region 4 on the curve that we showed earlier would be the cause of all the temperature difference. Okay. So the thermal resistance of more important consequence would be actually in this particular case only the region 4 as can be illustrated in this particular figure here. So having said that, let us look at what is going to be the surface temperatures. So what is going to be the solidification time that such a process would actually need. So if a large slab shaped casting is produced in thin water cooled mold made up of metal, say copper, having much larger conductivity than the solidified casting, then the thermal resistance provided by the interfacial region between the solid and the mold would kind of be eliminated. Okay, it is insignificant almost. So in such a case the predominant thermal resistance would be offered by the region 4 as I had just shown. So neglecting the thermal resistances of all the other regions, the temperature distribution at any instance takes the shape shown in the figure below right here. Okay. So here the mold metal interface or the casting surface temperature theta 0 theta s can be assumed to remain constant in time, particularly because the mold is also water cooled. Okay. So you have a completely water cooled thin mold. So obviously there is going to be a constancy of the surface temperature of this particular metal. So let us assume that surface temperature to be theta s equal to theta 0. Okay. And let us also assume the freezing temperature to be theta f, which is not different than the pouring. So pouring and freezing are same. So it indicates the freezing temperature of the metal, and at any instance t, delta t indicates the depth of solidification. As you can see, particularly here, this is the solid liquid front and it is moving ahead at d delta t by dt, and delta t is the instantaneous thickness of the shell which is being developed here, solid shell, and the process can be idealized without much error as a one dimensional heat transfer problem, particularly because we are having almost a heat sink as a mold because it is a water cooled mold, and so therefore the heat transfer would be typically one dimensional. The maximum resistance, thermal resistance, which is offered to this liquid temperature, the freezing temperature, is really the solidified portion of the mold, and the other end of this is really a constant temperature surface or constant casting surface temperature theta s. So let us see in this kind of a problem what really happens, or what would be the estimation of the solidification time. So let us estimate the solidification time Ts. So we get that delta at Ts should be really equal to half the thickness of the mold. We assume mold thickness here or casting thickness here to be equal to h. So therefore there is heat transfer from both sides of the casting. So therefore h by 2 is really the plane along which the solidification fronts from both sides would propagate and stop. Okay. So the temperature profile within the range x varying between 0 and delta t is given by theta minus theta s divided by theta infinity minus theta s equals the error function of x by twice root alpha s t. I think you had earlier talked about this in details when we did the thermal conductivity and temperature distribution across a sand mold. So, I am not going to illustrate how this equation came, or you already know that it was from a singularity variable analysis and one dimensional heat transfer problem, which we actually solved to obtain in the case of sand mold. Okay. So, in this case I will just mention that theta infinity is an integration constant, and we will not bother about it because ultimately we need not use this value for our calculations. Okay. So, this is a constant of integration. If you remember the whole process of the solution, there were many integrals which were formulated in order to estimate the real value of theta, and alpha s basically is the thermal diffusivity of the mold, which was actually also recorded as the thermal conductivity of the mold per unit density times specific heat capacity of the mold. So, at x equal to, let us say delta t, theta, the temperature is actually the freezing temperature, right, theta f. So, if I were to put this value of x and theta in this particular equation, we have the error function of delta t by twice root of alpha s t is estimated as theta f minus theta s by theta infinity minus theta s. Mind you, this is the casting surface temperature. Okay. You are assuming that the mold is water cooled and acts as a sink. So, this actually cannot change because the freezing point and the casting surface temperature are similar. So, are the constant of integration theta infinity and theta s. So, therefore, this is really a constant. Okay. Let us call this constant lambda. So, we now have then the error function of x by twice root of alpha s t equals to lambda. Further, let us x equal to delta t. So, further let us assume that there is another ratio defined as zeta, which is actually equal to this delta t by twice root of alpha s t, or in other words delta t is basically zeta times of twice root alpha s t, and we have the term written as error function of zeta equals lambda. Once again, we find that the depth of solidification varies as the square root of time, as you can get an illustration here. Now, the constant zeta has to be determined in order to find out the time of solidification, okay, from these two relationships which are here. So, let us consider the rate of energy flow or the energy balance at the solid liquid interface. We have Ks del theta by del x, x equal to delta equals rho m L d delta by dt. So, obviously, at this front delta, which is the this is the mold, this is the solid part, and this is basically the liquid part. So we are talking about this x equal to delta as a function of time. So if there is a temperature gradient d theta by dx which exists at x equal to delta, that times of the thermal conductivity of the solid Ks should be equal to the total amount of heat rate that is liberated because of the moving front. We assume that at instance t, this front is moving at a rate d delta by dt. So the area terms get cancelled here, areas are on both sides actually. So you have the rate of change of volume times of the specific heat, the latent heat. Okay, so that's times of density is basically the total amount of heat rejected out of the solidifying metal, and Ksa del theta by del x at x equal to delta, the total amount of heat which comes out of the liquefied metal into the solid liquid boundary. So they should be heat balanced. So Ks here in this particular case is the conductivity of the solidified metal, and this can be written down as alpha s times of rho m times of Cs. Cs is the specific heat capacity of the solidified material, and rho m is the density of metal which is same in solid and liquid state. Okay. So this is the unified density, does not change much with respect to solidification at the freezing temperature. So therefore the del theta by del x should be defined as from, or should be defined from the equation that we had considered earlier for the theta right about here. Okay. So here we had the theta to be equal to theta s plus theta infinity minus theta s times of the error function of x by twice root of alpha s t. Okay. So from here we can calculate del theta by del x as theta infinity minus theta s times of d by dx of the error function of x by twice root alpha s t. Okay. So let me just write this down back here again, just borrowing it from earlier equation. So theta infinity minus theta s times of d by dx times of the error function x by twice root of alpha s t, and therefore this can be defined as theta infinity minus theta s times of 1 by twice root alpha s t. I am going to just differentiate this error function times of again 2 by root pi exponential to the power of minus x by twice root alpha s t square. Okay. So that is how the error function is differentiated. I think I had mentioned it in the last lecture, and so this really can be put back into the equation that we were doing earlier as Ks times of del theta by del x at x equal to del. We can actually put this as Kx by root of alpha s times of theta infinity minus theta s times of 1 by root pi times t, okay, exponential, and this becomes minus del by twice root alpha s t square, and that can be equated to rho m l d delta by dt. Okay, in order to find out what is going to be the d delta by dt in this particular case. So we can substitute the value of alpha s here as root of Ks by rho m Cs, okay, where again it is a thermal diffusivity of the solid phase. So it can be defined as the thermal conductivity of the solid phase per unit the density of the solid or liquid metal similar to each other times of the specific heat capacity of the solid phase. Okay. So, this we substitute for theta infinity minus theta s. So, that is what we substitute the equation, and delta, which earlier was twice zeta root of alpha s t from what we had concluded here earlier. Okay. So, we had assumed the zeta to be delta t by root of twice alpha s t. So, when we substitute this back, let us see what is going to be the final form. So, the first thing that I would like to get is an expression for d delta by dt from this term. So, d delta by dt becomes equal to twice zeta being constant root of alpha s divided by root of t this goes away. So, we are left with zeta root alpha s by root t, and on the other hand we have the from equations done earlier here, we have that the theta minus theta s really is a function of theta infinity minus theta s error function of the term zeta. Okay. This was zeta corresponding to x tending to delta, if you may just remember. Okay. So, if I just substitute this value here on the expression which I formulated in the last step, this expression right here, let us call it equation 1, then we have Ks rho m Cs whole under the root times of theta f minus theta s by the error function of zeta times of 1 by root pi t e to the power of minus zeta square times of rho m L zeta root alpha s by root t. So, basically on one hand we are substituting the value of delta, okay, d delta by dt from this expression here, and on the other hand this term theta infinity minus theta s is replaced by theta f minus theta s. So, therefore, this is how the expression gets formulated after the substitutions of these two values respectively, the d delta by dt and the theta infinity minus theta s. So, I will just now condense this expression and write this as zeta e to the power of zeta square error function of zeta on one side, okay, is equal to theta f minus theta s by root of pi C s by L. So, typically if we wanted to find out what is going to be the value of zeta, so zeta, as you already are aware, is basically delta t divided by twice root of alpha s into time t, and this delta tends to h by 2 if the casting is completely solidified. So, the zeta here would typically be equal to h by 4 root of alpha s t, or if I am able to find out the value of zeta, all I need to do is to do zeta square equals h square by 16 alpha s T s, and obviously when delta is h by 2, t becomes T s, that means it is solidifying the whole casting at that point of time, and the T s becomes equal to h square by 16 alpha s zeta square. So, the trick here really is to find out what is this zeta from this equation right about here, and this would need estimation through numerical integration method, and there are standard tables which have to be obtained for the error function corresponding to the different values of zeta, so that the left hand side and right hand side of this equation 1 can be obeyed. And from that you can have the time of solidification as the square of h divided by 16 alpha s. Mind you, this is the thermal diffusivity of the solid part, which is Ks by rho m Cs. You had earlier seen how we had substituted it into the expression times of the square of zeta. Okay, let me just write this in a little proper manner here. Okay. So, this is times of square of zeta. So, I think we now can iteratively sort of estimate what is going to be the solidification time, and we will see in this particular case also numerically how the time is going to get varied because of this constant casting surface temperature. So, in the interest of time we will close on this module and probably explore a little more of these processes in the next module. Thank you so much. Bye bye.